What happens when a process becomes dangerous faster than an operator can react? An emergency shutdown system, or ESD system, is designed to recognize that condition and drive the plant toward a predefined safe state. Keep one picture in mind: a chain with 3 links: detect, decide, act. If any link cannot do its job, the shutdown may not succeed. The first link is detection. Independent instruments watch critical conditions such as pressure, temperature, level, gas concentration, flame, or equipment speed. A manual ESD push button can also start the trip. These initiating devices watch, or report, conditions identified as hazardous. The second link is the safety logic solver. It receives the input signals and compares them with the configured trip rules. If the rule is met, it issues shutdown commands. The logic solver is normally part of the safety instrumented system, separate enough from the basic process control system that a control system fault does not defeat the protection. The exact independence depends on the plant design and applicable requirements. Some trips use one sensor. Others use voting, such as 2 out of 3. Imagine 3 pressure transmitters watching the same vessel. In this 2 out of 3 example, one transmitter reaches high pressure. One vote alone does not yet satisfy the configured trip rule. When a second transmitter agrees, 2 out of 3 inputs now confirm the trip. The logic solver can act even if the third channel disagrees. This arrangement can reduce nuisance trips caused by one bad reading while still allowing the function to act when a real hazardous condition develops. Voting is a design choice, not a universal ESD rule. Inside the logic solver, a cause and effect rule connects the confirmed high pressure cause to defined effects. Close the inlet shutdown valve and stop the feed pump. Here's a quick check. A separator reaches high pressure. 2 of 3 pressure transmitters vote to trip. What should happen next? A. The DCS only displays an alarm. B. The safety logic solver commands the final elements to move the process toward its defined safe state. C. The operator must first confirm the trip. The best answer is B. The DCS may display the event, but the protective action must not depend on a slow operator response. Follow that trip through the equipment. The transmitters detect high pressure. The logic solver confirms the voting rule, then changes its safety output. That output may de-energize or energize the required circuit, according to the design. In this example, a solenoid de-energizes and vents instrument air from the valve actuator. Stored spring force then moves the shutdown valve to its trip position. Position switches report whether the valve actually reached that position. At the same time, pumps or heaters may stop and alarms appear for operators. The final elements, not the controller alone, physically change the process. A shutdown valve may close, a blowdown valve may open, a pump may stop, fuel may be isolated, or several actions may occur in sequence. Safe state does not always mean everything is off, and it does not mean every valve closes. Many systems use de-energize to trip because loss of electrical power can then drive an output toward the intended safe condition. But this is not automatic proof of safety, and it is not suitable for every function. An alarm asks an operator to respond. An interlock or trip acts automatically when its conditions are met. The DCS often shows status, sequence of events information, and alarms, while the safety system performs the safety logic. After the process is safe, reset does not mean restart. Operators first identify the initiating condition, verify that the hazard has been removed, and confirm final element status. A latch trip prevents quiet restart when a measurement returns to normal. Diagnostics can reveal some faults, but proof testing is needed to uncover dangerous hidden failures across the complete loop, especially in sensors and final elements. Bypasses and overrides require strict authorization, indication, time control, and restoration. Remember the 3-link picture: detect the hazard, decide with safety logic, and act through final elements. Then verify that the plant reached its defined safe state. Never operate, bypass, reset, or test an ESD from a video alone. Follow the plant SOP, PTW, isolation, depressurization, venting, draining, PP, LODO, approved proof test procedure, and supervisor instructions.